So next, let's look at the redistribution from the RIP process into the OSPF process. So up to this point under RIP, I said redistribute OSPF 1, metric 1. Now I'm going to go from RIP back into OSPF. Now, since router 4 is in area 0, this is not a stub area, it should mean that when router 4 originates these routes, these are going to be type 5 LSAs, which are either the E1 or the E2 routes. By default, the route type is going to be external type 2, and the default seed metric is 20. So on router 4, if we simply go to the OSPF process and say redistribute RIP, the default metric will be 20, and the default metric type will be 2. But notice the log message that comes up here. It says only classful networks will be redistributed. So in OSPF version 2, as a backwards compatibility, it has this keyword for subnets, which is not enabled by default. So if we simply say redistribute RIP, it means that only classful summaries, so class A networks that are /8, class B networks that are /16, and class C networks that are /24 would be included in the OSPF database. Now, generally, we're going to have more subnets or aggregates that are not classful summaries. So 99% of the time, we would want to say here, redistribute RIP, then the subnets. The end result of this is that router 4 should be originating anything that shows up in the routing table as RIP, plus the connected interfaces that are running RIP, into the OSPF database. So if we look at the show IP OSPF database, and look at the type 5 AS external link states, it says the advertising router is router 4 for these individual routes. So the link ID field, this is the address. The advertising router is the router ID of router 4. Then if we were to look at the details inside of the database, it's going to tell us what is the subnet mask, what is the metric, and what is the metric type. So on router 4, if we look at the show IP OSPF, database for the external LSA with the link ID 30.0.0.0, it says that this particular prefix was originated by myself. I am the advertising router. The link state ID, that's the address. The network mask is the subnet mask. So it essentially means that this prefix is 30.0.0.0/16. The metric type is 2 by default. This means that this is an E2 route. The default seed metric is 20. So this should now mean that all routers in the OSPF network are going to see the prefix 30.0.0.0/16 installed as an OSPF E2 route with a metric of 20. So if we were to go anywhere else in the topology, let's say we look at router 6, and on router 6, we look at the show IP route OSPF. We see that the 8 routes that router 4 was learning as RIP, plus the connected interface, which is the 204.12.28.0/24, these are now being learned as OSPF E2 routes. They all have a metric of 20 and all have an administrative distance of 110. Now, if we look at the specifics of any of these routes, if we show IP route, then the exact match, let's say 204.12.28.0, router 6 says that the metric is 20, the type of route is an external 2, and the forward metric is 1 to get to this particular ASBR. So as I mentioned previously, the difference in the calculation between the E1 and N1 routes versus the E2 and N2 routes is that the external type 2s separate the metric fields into the seed metric plus the metric to the ASBR. So essentially it means here on router 6 that in order to get to router 4, my cost is 1, because this is going over a directly connected fast Ethernet interface. If we were to go multiple hops away, if we were to look at this from switch 1, from router 3, or from switch 3's perspective, we should see that they're learning the same route with the same metric value. So everyone should install this in the routing table with a metric of 20, but the forward metric is going to increment depending on how far away they are from the ASBR. Now, the only time, again, that this is going to matter is that if there are multiple exit points between the two protocols, if there is a tie in the metric of the E2 routes, then we're going to look at the forward metric as a tiebreaker. So in this particular topology, if router 4 were to redistribute the route from RIP into OSPF, redistribute it from RIP into EIGRP, then router 3 redistributed it back from EIGRP to OSPF, now we would have multiple paths in order to reach those external routes. There's going to be the set of E2 routes that are originated by router 3 and the set of E2 routes that are originated by router 4. Now, which one the OSPF routers are going to choose would then be based on their distance away from the ASBR. Now, assuming that all of these interfaces have the same cost, since they're all fast Ethernet, the VLAN 146 interface is going to have a cost of 1, the VLAN 67 is a cost of 1, the link between switch 1 and router 3 is going to be a cost of 1. Essentially, it's going to be a hop count. This should then mean that router 6 would choose the route through router 4, but switch 1 would choose the route from router 3. Because although the seed metric is the same for both of them, it's going to default to 20, router 6 would say the forward metric to go to router 4 is 1, versus the forward metric of 2 to get towards router 3. Then likewise, switch 1 is going to say the opposite. It would say my forward metric to reach router 3 is 1, my forward metric to reach router 4 is 2. Since there's a tie in the two metric values, then I'm going to use the forward metric as the tiebreaker. Now, if we were to set these as to external type 1 routes, then there's no differentiation between the metric and the forward metric. Switch 1 would simply install that in the routing table as the 20 plus whatever the cost is to the ASBR. So switch 1 would say that the cost is 21. Then as we go to switch 3, since this link is a cost of 1 to get to switch 1, it would say its metric is 22. So again, the only time that this really matters, what the metric value is and what the metric type is when there are multiple exit points out of that particular protocol domain. Now, we can also use this for the purpose of traffic engineering based on the route type in the OSPF path selection state machine. So as we talked about before, when OSPF does its path selection, it's always going to choose an intra-area route over an inter-area route over E1 over E2 over N1 over N2. So this is regardless of the administrative distance or of the metric. This would then mean if I wanted to prefer router 3 for certain destinations versus router 4, on router 3, when I do redistribution of EIGRP into OSPF, I could say set the metric type to E1. On router 4, when I redistribute from EIGRP to OSPF, I could leave this as the default metric of E2, metric type of E2. So in this case, regardless of what the cost is to the ASBR, or regardless of what the cost that's advertised as the seed metric, router 3 would always be used as the exit point to get to the EIGRP network, because the E1 routes, they always have to be preferred first over E2. But again, if the only device you're doing redistribution is router 4, then it really doesn't matter what the metric type is or what the metric is. Because if the only physical path to get to the RIP domain is this way, then regardless of what values are installed in the routing table, that's the physical path that the traffic is going to follow. Now, once our redistribution is complete here, the next step that we would want to go through in our verification would be to test, can I actually reach the destinations that are learned from the other protocol? So at this point, we're redistributing just between RIP and EHRP on router 4. This means that ideally I should be able to go to switch 3 and send ICMP pings to any of those destinations learned from BB3, and I should get a response back in. So of course this would assume that we're not doing any type of application filtering, like pings are denied somewhere in the transit path. But with no other features configured, just the normal routing and the normal redistribution, switch 3 should be able to reach any of those prefixes learned from RIP. So if we look at the command line on switch 3 and look at the show IP route, and I'm going to look at just the E2 routes. So show IP route include E2. These are the ones that were redistributed from RIP into OSPF. If I were to ping 30.0.0.1, we see I get a response back. Okay, if I ping 204.12.28.4, which is router 4's address, I get a response back in. .254, that's BB3. So this is now verifying for me, not only did router 4 perform the redistribution both ways correctly, the devices in the RIP domain are learning about the OSPF routes, and the devices in the OSPF domain are learning the RIP routes. So for the vast majority of the redistribution checks, this is going to be our final verification. If we can reach the destinations, we can assume that the redistribution was correct. Now we'll see the problem that we're going to run into, though, is that if the routing table is very large, it can be very time consuming to check for each individual destination, do I have reachability to that when I'm sourcing the packets from different interfaces? Because on switch 3, when we look at the show IP route 204.12.28.254, switch 3 says that my outgoing interface, in order to reach this particular destination, is VLAN 79. So this then means whatever IP address I have assigned to VLAN 79, this would be the source address that I use for any packets I'm locally generating to that particular destination. So when I ping 204.12.28.254, it means those packets are coming from 155.28.79.9. However, this does not necessarily imply that this destination has a route back to the other interfaces on switch 3. So if we look at the show IP route connected, just because I have reachability to them when I'm sourcing traffic from VLAN 79 doesn't mean that's going to be the case when it's coming from the loopback or from VLAN 9. Now, likewise, it doesn't necessarily mean they won't have reachability. It just means that there's separate checks that we would have to go through. So if I want to see, do they have reachability to my VLAN 79 network, that's what this first ping is going to test. If I want to know, do I have reachability to them, and do they have reachability to my VLAN 9, I would need to change what is the source of the packets. So if I ping from VLAN 9, it means they have a route back to that. If I ping from the loopback 0, likewise it means they have a route back to that as well. Now specifically in this case, the reason why they do have reachability is on switch 3, if we look at the show IP OSPF interface brief, all three of those interfaces are already in the OSPF process. But if for some reason the loopback was not advertised or the VLAN 9 was not advertised, then devices in the RIP domain are not going to have reachability back to those segments. So the key point here is that unless we actually test that it works, there's really no way to predict what the reachability is going to be. So we could look at the the routing databases on each individual device and make a list of them, but usually that's going to be too time consuming. So one thing that we can do for verifying this type of reachability is to use the TCL scripting along with ICMP. So we'll see in our next couple examples, when we do run into problems with route feedback and traffic loops, using a TCL script to run through different ping commands is a quick method that we can use on all of the devices to figure out what destinations do they have reachability to and what destinations do they not have reachability to. Now, TCL stands for the Tool Command Language, which is an open source scripting language. It's not specific to Cisco iOS. Now, specifically, iOS supports version 8.3.4, which I believe there's some newer releases beyond that, but pretty much any functionality that we would need for scripting is going to be supported in that particular version. Now, since TCL is essentially a full programming language, 99% of it is going to be outside of our scope. So we're not going to talk about writing a lot of complex scripts today with TCL. What we're going to be using it for is just some basic reachability testing for automating these different ping commands to the destinations that we have installed in the routing table. Now, the only issue with this is that you have to know what the syntax is exactly, because there's not a reference for the syntax on the context-sensitive help or in the Cisco documentation. So here's an example of a basic script where first router 1 is starting the TCL shell. It says we're going to create a for loop and define a variable x. So for each value that x has, we're going to run the ping command for that particular variable's value. So the end result of this would be that router 1 is going to ping 1.2.3.4, then it would ping 5.6.7.8, then it would ping 9.10.11.12. Now, the reason that we would even want to do this in the first place is that if we were to do ping commands, let's say on switch 3 that we were just looking at, I want to ping 30.0.0.1, and I want to ping 30, was it 30.1 or 31? 30.1. So I want to ping 30.1.0.1 and 30.2.0.1, etc. So there's a bunch of different destinations that I want to ping. The problem is, if I take these commands and simply paste them into the console, you'll see that you're going to overrun the console's buffer. So when I paste this from the clipboard, the first command was run, ping 30.0.0.1, but while the iOS was trying to return this command to the exec prompt, two of the other commands were lost in the console's buffer. Now, when we do this with TCL, the difference is that the router waits for the command ping 1.2.3.4 to return completely before it issues the next one, which would be ping 5.6.7.8. So the vast majority of platforms, as long as their iOS version is relatively recent, they should support the TCL. And this is going to include most of the newer Catalyst iOS versions as well. So if we were to look at some device in the topology, let's say on router 6 or switch 1, and I want to test, do I have reachability to all of those routes that are being learned from RIP? So on router 6, the first thing I need to know is what are all the addresses that I want to reach. So if I show IP route and include the E2 routes, I want to test reachability to these 9 different destinations. So first off, I need to make a list of these. So I'll just take these into Notepad and paste them. Okay, the end addresses that I'm trying to test here are all the .1s. And then for that connected segment between router 4 and BB3, the address there is .254. Now I could remove the leading spaces here, but for most of the syntax, it's not going to matter if there's extra spaces there. Okay, so now I have the list of addresses that I want to test. Now in router 6, I'm going to start the TCL shell. I'll say for each variable that I'm defining, open braces, the list of addresses, close braces, and open braces on the same line. Whatever the exec command I want, in this case is ping, $, and then the variable name, followed by close brace. So we can see the result of this is that router 6 pings all 9 of these destinations, but it waits for the first command to return before it runs the additional ones. So now essentially we could use this same type of script that we wrote on router 6 and then use it on all of the other routers that support TCL. So basically our full script here would be for each, whatever variable is, the list of addresses, close brace, open brace, ping, $, X is the variable name, and then close braces. So if I were to try this from switch 1 as well, let's say TCL shell, paste that script in, and then it runs through all the pings. So based on this result, I can now assume that all of the routes that came from RIP were properly advertised into OSPF, and the routes from OSPF were properly advertised back to the RIP domain. Now again, this is not going to include testing the reachability from every source interface. So for example, on router 6, if I'm not advertising my loopback, when I do these pings, since router 6's route to get to this destination is via fast Ethernet 0/0.146, my pings are really only checking BB3 and the whatever routers are behind it. It's checking their reachability back to that particular segment. So if I had another interface, VLAN 6, that doesn't necessarily test that connectivity. So I would need to modify what the script says and change the source. So I'll say ping X, and the source is from my loopback 0. So we can see now router 6 is testing reachability to these. It says I'm pinging that particular destination, but now I'm changing what the source address was. It's now my loopback. So based on this fact, now that the pings are getting there and back, then I can assume that reachability back to that interface works as well. Now you can get really complicated with the syntax of the scripting, because as I mentioned, it's a full programming language basically. The other only thing you may want to know here is that if you want to run multiple commands, you can terminate the line with a semicolon and then run whatever other additional commands you want. So we could say that I want to ping from the loopback, but then also ping from, let's say, FA0/0.146, FA0/0.67, and then let's see on router 6 what other interfaces does it have. Let's say show IP route connected as serial 0/0/0. So now router 6 should do this from all 4 of those different interfaces. Where we can see basically BB3 has reachability back to all of those. Now if there was some address there that we didn't have reachability to, we would see this in the scripting output just because the command line is going to stop. So if I put this address 1234, this is not an actual valid address in this topology. So we can see simply based on the fact that the packets are being lost, I now know that there's a reachability problem to this destination. When you run into this case that the router is dropping packets because it doesn't have a route or there's some sort of problem, Now we need to cancel the script, otherwise it's going to keep running, and it may take it 10 minutes before it times everything out. So the way you can do this, if you're connected to the router through its directly connected console, just use the normal escape sequence, which is Control-Shift-6X. If you're connected through the access server, then the access server is connected to the router's console. You need to send the escape sequence through the access server down to that individual TTY line. And the difference is that instead of doing Control-Shift-6X, you do Control-Shift-6-6. So Control-Shift-6X would send the break to the access server itself. Control-Shift-6-6 is going to send it through the access server's line down to the router that's actually connected. So in this case, since I have multiple windows open, these are connected directly to the consoles, then I can just say Control-Shift-6X. But if I went to the access server and then did a reverse telnet to router 6, then I would have to say Control-Shift-6-6 to send the break down to that particular line. Now, there's a lot of resources for TCL that are going to be outside of our scope here. If you go to the main TCL website, which is tcl.tk, you can see all sorts of documentation there. There's also a specific book that is for iOS scripting on TCL. So it's just called TCL Scripting for Cisco iOS. You can see this one is available on Safari if you want to read through some of the portions of it, or you could buy a printed copy from Cisco Press or Amazon, wherever. Also, if you go to Cisco's website and just search for TCL, there's this document here that explains the basic functionality for the process. But when you look at their examples, the problem is it's not a lot of real good syntax that it shows you. So here it says TCL script using the show interfaces command example. It says using the TCL regular expression engine, scripts can filter specific information from show commands in a custom format. Following is an example of filtering show interfaces and creating a comma-separated list of BRI interfaces on the router. So you can see you'd pretty much have to know the exact syntax of TCL to do this. So there's a lot of flexibility that you can do with the iOS. Problem is you need to know the programming language to begin with. And the issue within the scope of the CCI lab exam is that TCL is not really an iOS feature. It's a separate open source scripting language. So this means that the documentation, it's not going to be on Cisco's website. It's going to be on the TCL website. So if you are going to use this technique for testing reachability in the CCI lab exam, then you're going to have to know this syntax exactly. Now, the other potential issue is that once you invoke the TCL shell, the TCL's command parser runs on top of the normal iOS parser. Now, what this means is that any commands you send to the router, they're first going to be processed by TCL, and if there's not a match for TCL syntax, then it's going to be passed to the normal iOS process. And the issue that you could have here is that if there's an overlap between a TCL command and a regular iOS command, then the iOS command is not going to be accepted. And a good example of this would be the set command in a route map. So let's say here on router 6 that we're trying to do some configuration in BGP where I'm trying to change the local preference of routes coming from a particular neighbor. So from a BGP implementation point of view, what I would need to do is create a route map. Let's say route map from BGP peer permit 10. Okay, in the route map, I want to change a BGP attribute. I'm going to set the local preference. So I'll say set local dash preference and then whatever value, 1, 2, 3, 4, 5. Now notice here there's an odd output from the command line where it returned the value 1, 2, 3, 4, 5, instead of going just back to the next prompt. If I also had said something like set origin incomplete, it's going to do the same thing. What this actually means is that with the set command, I'm not actually issuing route map commands. I'm creating an environment variable named local-preference and a variable named origin. So if I say now echo origin, or I might have to say echo $origin. Let's see, echo origin. Let's try puts. So different versions will be a little bit different in the syntax here. So it says the value of the variable origin is the string incomplete. The problem now, if we look at the result of this in the running config, if we show run begin route map from BGB peer, it didn't actually take any of those values that I input. So where I wanted it to set the origin to be incomplete, I wanted it to set the local preference to be 1, 2, 3, 4, 5. It's not actually doing that. It's creating variables named local-preference and a variable named origin. So the way that you can get around this is just that when you're done with the TCL shell, when you're done with your ping script, just say TCL quit, and that's going to exit the process. Now we could see that the TCL shell hadn't exited because when I invoked it and then later went to global config, went to the interface level, from here it doesn't look like there's any problem, but if I type end or do Control Z, it goes back to the TCL parser. So just be aware that the TCL parser comes first before the iOS parser. So for any overlapping commands, it's going to go to TCL instead of the regular iOS syntax. So to avoid that, just when you're done with TCL scripting, either type TCL quit or exit to leave the exec process, which is then going to terminate the TCL shell.